So distributed software engineering isn't particularly hard to define, but I have quite a few slides before I can really explain it in depth. So for now, just consider DSE to encapsulate all of the activities where software engineers work remotely, like they work from home. And remember that initialism DSE. So you can save questions for the end of the presentation, and the top right of each slide has a slide number. So feel free to save and reference those. But without further ado, I kind of want to talk about my motivation for researching this topic, if possible. There we go. So in the fall of 2019, I landed myself a summer internship at a company in Madison. I spent December through February preparing for the job, and I was learning new JavaScript frameworks, figuring out my living situation, and so forth. And then March 2020 happened. You know, those couple months until June aren't ones that I particularly want to relive, and you probably don't want me to either. So I'll skip that part of the story. But luckily, I did still end up with the internship, albeit from my parents' basement instead of in Madison. The team that I was placed on was rather large. It was about 10 people, and that's intimidating in itself. But working from home meant that it was even harder for my teammates to get to know each other and for me to get to know them. And I'm sure that many of you can relate to this experience, and if not, then you know, at least you can relate to the experience of working remotely, because we've all been doing it for the past year for school. Anyways, the internship actually went great, but for all I know, you know, I didn't get to know my coworkers. For all I know, they could have been centaurs or Terminator T-1000 clones, or even attached at each other's waists. Now, obviously I'm exaggerating, but I was really left wondering what aspects of remote work truly impact traditional software engineering. So when I started looking into the topic, one of the first papers that I came across actually freshly detailed the experiences of over 3,500 software developers and program managers at Microsoft. These employees, who previously worked in person in King County, Washington, were surveyed twice in the spring of 2020 after being sent back to remote work from home about their productivity. The respondents rated their perception of benefits and challenges of working from home and the effects of each on their productivity. The authors aptly named their paper by quoting Charles Dickens' A Tale of Two Cities. They stated, "It was the best of times, it was the worst of times." That is, they're highlighting the dichotomy of experiences found in their research. So like you can see on the slide, many of the factors uncovered were seen as a benefit for some employees and a challenge by others. The factors that I've listed were found to have statistically significant impact on self-reported productivity, either positive or negative, and it's the same factors here. So some people experience more distractions during remote work than they did in the office, and some people experience less. Obviously, the results of this paper can't be used to theorize much about planned shifts to remote work, since these employees likely weren't planning for a pandemic. However, in this paper and another similar one, that provided me inspiration to look deeper into the topic of distributed software engineering. So I actually began a literature review all the way back in October for my human factors engineering course. And I had to complete that paper in December, but I felt unfinished. So I'm glad I kind of got to continue my work for this course. The first thing I did was search for information, and it took some time, but I ended up focusing on literature published after the year 2000 that was written in English. And it seems simple, but I want to make sure that older work and non-English work is no less important. I just wanted to study the current happenings of things that I can actually read. So I used a variety of databases and catalogs, and even ended up emailing authors when I couldn't find their paper for free online. And I ended up using a tool called Zotero, which I would highly recommend to collect and organize these papers. The graph on the right is a citation graph, and it shows the major literature that made it into my final paper. Each arrow points in the direction of a paper being cited. So this isn't really necessary, but it's a cool graph, and I kind of wanted to show off. So there are hundreds of more papers that I really could have read, so I'm not going to pretend like I know everything about current research in DSE. But I think I've synthesized some good conclusions that everyone can take away. Specifically, here's what I want to pass on. By the end of the presentation, I hope to have taught you 4 major things. First, a general framework that can help everyone stay on the same page when discussing this weird human process called collaboration. Secondly, a formal understanding of what distributed software engineering is. It's really not that complex, but there's more to it than just remote work. And thirdly, you should be able to recognize that the vital connections that exist between collaboration and distribution in software engineering. Lastly, I want to make sure that we can all make objective and effective decisions in our careers, because I bet that all of us will eventually be working in some distributed setting. I'll pop this slide in a couple more times to keep us on track. So let's move on to the more preliminary slides before fulfilling that first learning outcome. I want to start here with a quote from an experienced educator, Dr. Luis Capretz. So he says, "Software is a byproduct of human activities that incorporates our problem-solving capabilities, cognitive aspects, and social interaction." So that's right, we're not just code monkeys pushing buttons. Software engineering is a very socio-technical activity entrenched in human-centered design. And human-centered design is like a sustainable approach in software engineering that addresses ergonomics regarding users, developers, and other stakeholders. So and software engineering involves human factors of those people. However, we, as noted by plenty of authors, we as software engineers kind of tend to forget about the developers part of human-centered design and like to focus on the users and stakeholders instead. So of course, we want to work together in a way that fulfills both business and personal needs, yet we spend a lot more time worrying about the technology and stakeholder needs than how we as software engineers work together. As Capretz also said, software professionals should also delve into non-technical issues and recognize that the people involved in the software development process are as important as the process and the technology itself. So the trope that developers work best alone isn't really just a meme. You know, there is a natural affinity, or maybe not natural, but there is an affinity for more introverted people to make their way into computer science. You know, research has shown that. But and there's nothing wrong with that. I fit in that category myself. But also, there are human capabilities that we can be mindful of and develop. And there's evidence that such capabilities can be very impactful. A study out of Madrid utilized some occupational psychology methods to identify the best roles for software engineers based on their personal capabilities. They identified some major groups of capabilities as intrapersonal, organizational, interpersonal, and management. The specific capabilities for each group are listed on this slide, but you don't need to remember them. I know there's a lot there. Now, these capabilities are not distinct personality traits. Occupational psychologists have recognized and continue to argue about the personality traits that influence a person's likelihood to have these capabilities. But all of these capabilities can be developed through learning and training. The researchers for this study worked with managers and project leaders to interview engineers, identify the most important capabilities for roles in those managers' purview, and match engineers to such roles. There was room for flexibility when deciding a person's role, and so managers didn't have to like strictly stay to this criteria that they set up, but they continue along with that for 6 months of deployment. And as you can see, their results indicate that the use of their capability-based method for choosing roles actually resulted in a mean defect rate that is 47% less than the projects of using traditional role assignment procedures. This is only one study, but the research is notable for a few reasons. The main point I want you to take away is that it's not only important for a person with certain human capabilities to be given a role in which they can strive in, but it is important to recognize that the human factors that all engineers bring to a team results in better collaboration for the entire team. It wasn't a single person or a few single people who were able to, on average, drop the mean defect rate by 47%. It was the team collaborating. So we can all develop those capabilities, and and so forth. However, if the larger picture shows that the effects of collaboration between people with these skills is what's important, then how can we define collaboration? The model that you see on the screen here is the 3C model for collaboration, or just the 3C model. It lets us pull out a microscope and describe the smallest, most important parts of collaboration. A great majority of the papers that I reviewed use these three terms, the 3Cs, interchangeably or without defining or citing anything, and it was frustrating at some points, but I ended up, finding a couple sources here that do define them and model them. So how I describe it is based on my understanding of that literature. The graphic on the screen is derived from a paper that models collaboration as a basis for groupware development. Well, if you don't know, groupware is generally any software that's purposed to help people achieve some goals for a shared set of tasks. Now, software engineers working remotely need to achieve some goals for shared tasks, and they do so using software. So even without using this model for its direct defined purpose, it provides a perfect way to describe collaboration in distributed software engineering. So to understand it, let's talk about what drives what here. Communication in the top left involves the exchange of information between people. It's that simple. In a formal setting, most communication involves the creation or resolution of commitments. Now, creating commitments like schedules or tasks requires context and resources. You need to understand what's going on right now and what can be used to make something happen in the future. So coordination is the activity that involves the organization of such commitments. Now those commitments are made through communication and organized, and the activities around coordination are still involving planning, but a lot of it's organization. The actual realization of those commitments, so doing the tasks or meeting the schedule, comes by means of cooperation, where people execute commitments from the same pool from their team. Commitments are shared, and in that way, then obviously communication is needed for two people to cooperate on a shared commitment. However, if it is also common that if a commitment needs to be changed, the task or schedule needs to be changed, then it begins a whole nother cycle of these 3Cs. So in totality, the actions performed here and the resources managed during the cycle make up collaboration. And I realize I just threw a bunch of words that start with the letter CO, so I want to run through an example. So Alice and Bob here are in a software development team together. They work in the same office, so they have the similar computers and equipment, and on those computers, they have similar software like IDEs, project management tools, maybe communication tools like Microsoft Teams, among others. They also have shared resources, such as printers, meeting rooms, and document storage. When Alice and Bob want to communicate, they usually do so face-to-face in a regular software engineering setting. This is a rich form of communication. They can see and hear each other in real time. Information can be shared via something like a projector or on paper or on the monitor at one of their workstations. So when Alice and Bob meet, they can create or they can generate these commitments by speaking to each other while accessing, displaying, and creating information through these mediums here. There's also other mediums. For example, they can whiteboard ideas or schedule events on a calendar, write stories in Jira, or maybe just exchange thumbs up. Body language is a perfect form of communication, as one of the richest forms. They store the commitments in whatever mechanism works best, be it physical or digital. And when Bob or Alice wishes to complete a commitment, they can access its information from the coordination mechanism in which they stored it. And whether or not they complete the commitment individually or together, they are cooperating because their team owns the commitment, not an individual. So it's vital that they can communicate with each other if that commitment needs to be changed or if they need help. I hope this makes a little more sense now. And again, in totality, this is collaboration, and breaking it into these simple parts makes it so that we can later describe the impacts on collaboration due to software engineering. But of course it can't be that simple, and I'm sorry for misleading anybody. We must also think deeper about the relationships between communication, coordination, and cooperation, the 3 C's. So what else is required for effective collaboration between software engineers? In the basic model that we've gone through, we can identify how they create, change, and realize commitments with the team. However, calling it a defined cycle is kind of just oversimplifying how life works. We're all humans, and we each have different human capabilities, and we each have our own view and interact with the world differently. So, not everything is a cycle like this. And in order to effectively work together, we must at minimum also have the awareness of our surroundings and trust of the people in it. It seems unlikely that an engineer would be able to create, change, or realize commitments with their team if they were unaware of their teammates' roles or what their teammates are doing, and especially if they were unaware of the resources needed to complete such actions. Maybe it seems obvious, but there are layers to it. Hand in hand with awareness is trust, interpersonal trust. So trustworthiness is made up of like expectations about a person's behavior in certain contexts. You can have positive or negative attributions of trust that affect your view of someone's trustworthiness. If you make something called a fundamental attribution error, you are attributing trust to someone based on a personal characteristic of them instead of an event. So trust requires awareness, and with that, awareness requires trust. Now, this model here doesn't originally include trust in the picture here. However, other models do, so I really wanted to show it. There are bigger aspects of awareness here. So while the authors of that model don't really dig very deep into awareness, this still falls in line with it. So the authors that describe awareness in this way, or in these ways, quote, they describe how an integral part of software engineering is like the development and maintenance of a shared understanding concerning the state of software projects, tasks, artifacts, and activities, and the expertise of developers working on the project. So collaboration is also needed to develop and maintain this shared understanding and the understanding that each person has. So we can synthesize from surrounding literature that development of that awareness information is in turn fostered by attributions of trust, and it is needed for proper collaboration. There are 5 types of awareness here on this slide that are relevant to group dynamics that exist in general collaborative work, but these are especially created for distributed software engineering. The first one, informal awareness, is involves knowing the presence of people, what they're doing, and some insight on what they're going to do. It is needed to appropriately initiate casual communication with others, like asking a quick question to someone in their office. Next, group structural awareness is associated with knowing what commitments teammates have, how they're doing on them, and why they're the person that are doing those commitments. This awareness fosters the development and use of expertise, and it lets the right person get the right task. Social awareness is needed to minimize conflicts in a team. It provides insight about relationships that exist between collaborators. It is generated over time and is especially intertwined with culture. Next, workspace awareness concerns information about teammates' interactions with the shared workspace. It's similar to informal and group structural awareness, but this type of awareness involves the state and recent history of resources and commitments, not the people that are interacting with them. The last type of awareness is context awareness, which cross-cuts the other 4 types. That's why it's meta-awareness. All of the awareness changes over time, right? You learn new things, your understanding changes, and context awareness is the ability to be aware of the changing context of that awareness. It's awareness of awareness. I know it seems odd, but it adds kind of a time factor into all of this. All right, so that's collaboration. I know it's a lot. However, the basics of it are the most important parts to understand. software engineers must communicate in order to create and realize commitments that they make to their team. They must use mechanisms of coordination to plan, organize, and select those commitments. And given that the commitments are made in a shared workspace, they do not just operate on them, they cooperate. Any collaborative activity requires timely awareness of the people and resources involved in it. And just the same, that awareness can only evolve with collaboration. So in the future, when you think of collaboration in your career, try to consider the model that I've laid out here. I know I realize some of you are probably thinking, I thought this was supposed to be about distributed software engineering, and you're right. So let's move on. As you probably already guessed, distributed software engineering doesn't just mean remote work. If it did, I would not use such a long name for it. Some people have used the terms distributed software engineering, distributed software development, global software engineering, global software development, geographically distributed, etc., and other terms interchangeably. Now, there's actually some nuance to it, but for the sake of this presentation at the moment, distributed software engineering is a general term that can encapsulate all of that. However, the term is also used to describe software engineering of distributed systems, which is confusing because that's a completely different topic. So just stick with me for that. Sometimes semantics are weird. I want to first talk about the what. What makes software engineering distributed? Unfortunately, the growing field of study has no standard terminology or taxonomy. Many features described as part of DSE overlap across papers, and authors, like with collaboration, rarely define the terms that they use. This lack of standardization leaves research fragmented, it leaves industry fragmented, and few people have really made a notable effort into untangling this web of terminology that's kind of evolved without regulation. I did read 2 papers that contain explicit descriptions of DSE that I feel can be used to relate the intentions of many other papers. So through literature review and expert surveys, both papers describe distributed software engineering as a facet of geographic location and relationships involving inter and intra-organizational structures. That's a mouthful. So let's break it down using some defined terminology and a taxonomy that describes the relationships between those terms. The first level of DSE is location. It entails the locations that the engineering is distributed for the software projects, product, system, service, etc. Is it distributed onshore within the same country, or is it distributed offshore in another country or in multiple countries? The second level of this taxonomy is legal entity. This level is concerned with the legal entities involved in the software engineering. That is the project being insourced, where it's being kept in-house under the same company, or is it being kept outsourced, being developed in part by another company? These sourcing strategies can exist within a team or within a project. For example, onshore insourcing could involve a team made up of engineers who work for the same company, but in different parts of the country. It could also involve a project made up of teams based in different offices throughout the country. The same goes for offshore distribution. A team could be made up of individuals who are located in different countries and either work for the same company or maybe they're contractors. Similarly, a project could be made up of teams situated the same way. My point here is that not everyone has to be in different locations for software engineering to be distributed. It is the collaboration between people or teams that makes that distinction. The next level of this taxonomy is geographic distance. And the visual gets a little messy here, so you can focus on the parts that you enjoy of it. I wanted to represent it how it was originally given in the paper. The authors chose to distinguish geographic distance based on onshoring and offshoring. So you can see it's close and distant and near and far. And they wanted to do that because they really mean different things for onshore and offshore. If something's in the same country, close means something different than close if they're in different countries. So they use like airplane flight times as the distinguishing factor. So software engineering that is distributed onshore can either be of close or distant geographic distance between people or teams, and that means that no flights are needed, they can drive, etc. And distant means that it's like a domestic flight. Offshore distribution can either be of near or far geographic distance, where near is a flight that's less than 2 hours and far is a flight that's more than 2 hours. The last level is temporal distance. So in any distributed setting, there may be some time difference between engineers and their teams. The authors also chose to distinguish the differences in scale of temporal distance similarly as geographic distance. So they have similar and different for onshore and small and large for offshore. It's generally the same reasoning. So similar means that the time difference is less than or equal to an hour, and different means that it is greater or equal to an hour. And then in offshore situations, small and large would mean that it's 4 hours there, so less than or equal to 4 hours is small temporal distance, and large is greater than 4 hours. So maybe now you understand why I use the term distributed software engineering instead of global software engineering. Now, actually, I do want to get back here just a second and take a look and recognize that those criteria are kind of odd. And I want to say right now is that the purpose of this taxonomy is to be used to classify case studies in different papers. So it is to kind of break up that fragmentation and break up this web of nonsense that's kind of been built up. But the paper does call it global software engineering in their paper, giving their argument as global as a reference to the globe or around the world, but around the world does not exclude within the same country, and hence we have chosen to use global software engineering. I'll be honest, I love the taxonomy, but with that same argument, I could say that all software engineering is global software engineering, and of course we need to draw the line somewhere. So to me, global software engineering is just international distribution. It involves offshoring. And I would like to kind of pass on this to y'all and to keep distributed software engineering as kind of the overarching theme. So that pretty much sums up what DSE is. And I know that was a lot shorter than describing collaboration. I know there are layers to DSE and it takes some time to remember, but the concept's pretty simple. It is more than remote work, but you kind of need to think in the sense of people and teams. So people, teams, and organizations can be distributed legally, geographically, temporally. Those three factors encapsulate most of the difference there with distributed software engineering. So we can move on to this third learning outcome and try to connect the understanding of collaboration and DSE so that we can uncover some impacts on software engineering associated with distribution. I want to go back to that example we had with Alice and Bob and see what kind of changes come with distribution now. So Alice and Bob are still in the same software development team together. They each have their own equipment and that is provided by their employer. And while there's probably some differences in hardware, they have a similar tool set for completing their duties, even if they work for different companies. It's a manageable difference. However, since they're working from different locations, they do not have access to the same shared resources that they would if they were in the same office. The vast majority of those services and resources that they share are just accessed on their computer now. It is also likely that their working hours are different because it could probably be in different time zones, and with enough distance between them, Alice and Bob may experience completely different cultures in their local living and working environments. This is workplace culture. This is general culture of if you're in a completely different country, this is something to be expected. So in many situations, people like Alice and Bob also work for different branches of a company or different companies entirely. And these factors and many more show that the power of distribution has over collaboration. So when Alice and Bob want to communicate in distributed software engineering, they aren't going to be able to do so in person very often, if ever. They require some technological medium, which creates barriers to and increases the complexity of collaboration. We can describe the need for adequate communication mechanisms in DSE in terms of media richness. So the richest communication medium is, of course, face-to-face. Individuals can see each other and hear each other with the greatest possible clarity. And as we talked about, body language can provide more meaning than speech can on its own sometimes. So even in a rich technological medium such as video conferencing, communication can actually be largely successful because both speech and body language can be prevented even with those barriers. DSE also allows individuals to select the richness of media for communication with more ease. So if Bob thinks that information is better suited for an email than a video chat, then he can send one without feeling weird about not just walking it over to Alice's desk because he can't. Likewise, being distributed also means that Alice and Bob can utilize rich forms of media that don't require synchronous interaction, like sending a video file. However, there are still exist important barriers here. Many researchers make the claim that even the richest technological mediums creates more ambiguity in communication than a face-to-face discussion. That is, information cannot simply be disseminated with the same clarity as face-to-face discussion. Distribution also increases the complexity of maintaining commitments. Information must be stored securely in a way that's accessible to both people, no matter where they're located. However, there is a reason why filing cabinets aren't used as often anymore. We still use, as software engineers, a lot of our coordination mechanisms are on computers anyways. But overall, when attempting to generate or resolve these commitments, the bandwidth for awareness is lower in DSE anyways. Thus, Alice and Bob are both more likely to fall victim to surprise breakdowns of cooperation. So with this example in mind and your newfound understanding of collaboration with the 3C model and the DSE taxonomy, you can pretty much make these connections on your own. There isn't a big list of impacts that distribution has on software engineering. I read quite a few case studies involving DSE implementation, and the parameters of each situation dictate how software engineers are effective. But we can use measurements of software defects in an empirical way to investigate the impact of DSE on software engineering. As I showed y'all earlier, assessing the effect of differences in collaboration by measuring software quality isn't a rare practice, like done with human capabilities. However, there's honestly really not many researchers that have done so in the realm of DSE. Now, I have limited time here. I don't have much more to show you, but I'm going to go over this a little bit quickly. So I've got out these 3 studies, and in the first study involved a case study on the change in quality over time for 2 medium-sized software products owned by a single company. So that's offshore insourcing because they were doing a handover between sites in Sweden and Russia. The specific locations were not mentioned, so these geographic and temporal distances can't really be defined here. Russia's rather large. So yeah, we can't do that. But software quality was investigated throughout multiple releases using measures for lines of code and cyclomatic complexity and code defects stemming from customer reports. However, after their statistical analysis, they found absolutely no indication that distribution actually impacted their software quality. Similarly, second is a really cool study that was conducted on the code base of Windows Vista, which was developed across 21 campuses across 3 continents. They analyzed the source code for software binaries and used those software quality measures, and again found there's not really significant evidence of adverse effects to quality because of distribution. Now, the third study was a little different. Yes, it is still insourcing, and it is matching the parameters in that situation. However, the quality measures, they were doing this on a large amount of embedded systems projects for a single company, so they didn't want to use post-release failures. They used failures found during system testing and integration testing, because post-release failures don't happen that often with real-time embedded systems, apparently because they have very high quality control mechanisms. Anyways, they did end up finding that there was statistically significant evidence that temporal distance reduces software quality, but not geographic distance. So empirically, the effects of distribution in software engineering are quite unclear. But not everything's not about numbers. So I want to touch on it real quick in this last part of my presentation. We've gone over the model for collaboration in software engineering and a taxonomy for distribution, and laid out some cool perspectives on the impacts of distribution has on collaboration. But to wrap up, I want to leave you with some final synthesis of success factors for DSC. There's a lot of researchers who have conducted creative explorations of challenges in DSC, and while many of them are not, a large majority of them are not empirical studies, their findings are still relevant and allow us to improve our understanding of collaboration in DSC. So these are 3 unordered success factors that are each identified by multiple applicable papers that I read. First, the freedom to choose a medium of communication is a central benefit of distribution, but it may require regulation to ensure that such choices result in a balanced and consistent mix of communication. So that's one of these success factors here that's been found. Secondly, since DSC is less conducive to the development and maintenance of awareness, there should be daily meetings purposed for sharing knowledge between team members or teams. This success factor is actually very commonly mentioned. And lastly, engineers should attend regular quality workshops where they can develop professionally, and they should take part in informal social meetings to mediate issues of social awareness, especially in culturally diverse teams. And managers should organize a trust building process, which itself is important especially for new employees. These success factors are not in conflict between papers, and their sources are diverse. So these are, agreed upon success factors. However, there are some other ones that are less commonly concluded, or there's conflicts. So the first one is that it might be helpful for individuals in distributed software engineering to follow a defined communication model. So I mentioned the need for some regulation on communication in order to ensure the effective generation and realization of commitments, but this factor just takes that a step further. There's only really a couple papers that I read that included this factor, but I thought it was fair to bring it up. The second one is actually a common one, but it's a factor in conflict. There are some papers that are even empirical-based studies that have found that there's not really a difference in team size as its effect on software quality and on collaboration. However, it is still really argued. And lastly, in order to form a more perfect shared awareness in DSC, all decisions should be documented and organized. And that last success factor brings me to my final conclusion. None of those 6 success factors that are particularly different than pre-existing accepted professional practices for software engineers. So there's this book called The Guide to Software Engineering Body of Knowledge, which actually influences our ABET accreditation criteria. And it has a couple relevant sections titled Group Dynamics and Psychology and Communication Skills. And each section contains conclusions that can be related to all of those success factors that we just went over. Interestingly, the book doesn't even really touch much on distributed software engineering at all. Now, I'm not trying to say those success factors don't matter. What I do mean is that these success factors actually make a lot of sense. They relate, these success factors that I've synthesized here from a lot of papers they relate to the accepted software engineering professional practices that already emphasize, they relate to pre-existing software engineering professional practices, and the success factors just emphasize the areas that are most impacted due to distribution. So to conclude, the field of distributed software engineering is growing, and I know that my job after graduation will involve me working in a distributed team. And it's likely that a handful of you will end up in one too directly after graduation. So before this presentation, everyone already knew that working remotely had some impacts on software engineering, and now hopefully everyone understands the finer details that can help them recognize the challenges in their future career. Yeah, that's pretty much what I've got. Thank you for listening to me ramble for 42 minutes. I'm going to scroll through all of my citations real quick and then go back to the beginning, and I can answer questions if there are